Hi guys, welcome back. We continue our video series where we investigate the collapse of the Florida pedestrian bridge. And in this video, I'll be going through and a little bit more in detail some of the theories that have been placed as to possible causes of the collapse, possible mistakes that happened, and things that were just not properly designed. Just a bunch of theories several theories that have been placed online that have been publicized and that people have widely begun to accept as possible reasons that the collapse occurred. And I am going to try to debunk those theories for you here today. Uh, that's this video. And before we get started, again, I'd like to thank all my subscribers. I think I'm up to about 67 or 68 subscribers, so each and every one of you, I'd like to thank you for signing up. It serves to motivate me to continue making videos. In addition to my subscribers, the comments that have been coming in and the feedback I've been getting, it serves to motivate me to continue putting out more videos and continue doing so in the future. So I really appreciate all your efforts. The comments have been really well written. Everybody's just really got a very firm grasp of what's happened. Everybody has a take on it, a different take. Many different takes have been put out there in the comment section, and just really just I'm impressed. So you guys are just really impressing me. So I have to say this quite an enlightened group that's involved here. So again, thank you for all the feedback, and so let's get started here. So first theory that's been placed out there is that the cable stays were intended to support the structure, and since they were not installed before the bridge collapsed, they were not there to support the bridge, so the bridge collapsed. So we know that a truss had been installed, and this one span had been installed, and the pylon, this center tower, and that's shown on the design drawings, had not been built yet. And we also know that the cable stays, these pipes that come down and intersect these panel points along the top cord, that they had also not been installed. So no pylon and no cable stay pipes. Alright, so now the theory's been put out there that, hey, those cable stays are missing and they support the bridge, and they would provide a level of redundancy. So let's dig deeper into that. We have these drawings here. Let's see how these cable stays actually looked close up. And there, on these drawings, there is a detail showing these cable stays. And looking at this detail here, we can see how the cable stay design is showing. So now, in a cable stay, you have what this bridge was showing to have, which is a steel pipe. In this case, it was a 16-inch diameter round pipe, and that pipe spanned from the pylon to the top cord panel point. If we look at the connection of this pipe, we can see that it was anchored to the bridge and also to the pylon with bolts. Alright, in this case we have, looks like they have about 8 bolts at each connection. Section A and Section B. Section A is at the top of the pylon, that connection, and detail B is at the top cord. And in both connections we have 8 bolts, 8 1 and 3/8 inch diameter bolts. Okay, so that's all that's anchoring that pipe to the bridge. So if this had been an actual cable stay, this pipe, you'd still have a pipe, but within this pipe you would have strands. This pipe really, in an actual cable stay bridge, is just intended to protect the strands. Now when I say strands, a strand is something like this. This is an actual piece of a strand. This is a 1/2 inch diameter strand. And these strands are typically what would be inside of a cable stay pipe, and I'm going to show you a cross section here if it'll show up. Each one of these strands has 7 wires. This one has 7 wires, and I think you can see it there. But these strands, you would have dozens of strands potentially in, depending on the size of the stay and the force that it was supposed to support. But these strands would be inside of this pipe. So here's a pipe, and here's a bunch of strands that are supposed to be in there. This bridge did not have that. All right, so really this connection is purely a decorative connection to keep the pipe positioned. If the pipe had strands in it and was actually supporting the bridge, the ends of the stay would have had much more. Would have had a much larger a detail here of concrete. There would have been a larger area of concrete. It would be a thickened area that would help distribute the force from the stay, especially at this top connection here. And then in the pylon itself, there may have been a saddle that would allow the strand to continue on to the other side. That's what, in my experience, I've seen that. I also believe they may now actually have strands that terminate at the pylon. But in either case, this detail is clearly showing that the cable stay was there just for a decorative aesthetic purpose. It was not really going to support it wasn't going to support the bridge. Now, in the proposal, the design build proposal, they state that these stays were going to prevent excess vibration, and that was the function that they, if any, that they were going to serve. What that means is when you have a, in this case, let's say a pedestrian moving load going across the bridge, that could create oscillations in the bridge, and depending on the number of people crossing and the rate at which they were crossing, that could create a vibration in the bridge, and these stays would limit that vibration. So I suppose you could, that's possible, but it's not a critical. That's not a critical feature for this bridge. So I don't. I mean, as you can see, cable stays are not really doing anything. These bolts. That's not a connection you would see in an actual cable stay. These strands would be anchored. They would have been post-tensioned, similar to what we've discussed previously in these diagonal truss members, where you had bars, not strands. You had bars. We had 1 3/4 inch bars in each of these diagonals, and in a cable stay, you would have had strands such as this. They would have been tensioned. They would have been anchored at least one end, and possibly if they went through the pylon and to the other end, you would have had two sets of anchors. So in this case, there's no strands, there's no anchors, there's no special anchors for the strands. There was no post tensioning of the strands. None of that had happened. So that idea that the cable stay was missing and the bridge had a lack of redundancy because the cable stays had not been installed yet, that is just not true. So the bridge was designed to be just a truss. The truss was intended to support all the loads. The pylon and the cable stays were purely decorative. They didn't have to be installed. They were just being designed for aesthetics, to make the bridge more of a landmark feature, to just make it look prettier. And it looks nice. They're sketches. It looks nice, the bridge with those stays. So I can't, in my opinion, the stays, they enhance the aesthetics, but structurally speaking, not significant whatsoever. So that theory is debunked. Theory number 2 is with regards to ABC construction method. So ABC stands for Accelerated Bridge Construction Method, and that's been called into question. Some of the online articles written have said that this collapse was possibly due to the ABC method, and that that there may have been a lack of oversight, or just something went wrong with the ABC part of the construction. So ABC, accelerated bridge construction, that just means that the bridge is built off-site and then moved to its final location. So in this case, the bridge was built off the side of the road, and then it was transported. It was spun, I believe, 90 degrees, and then it was moved along the roadway into the final position on top of the piers. So now ABC, that method is not that new. It's been around a while, and in fact, if anything, ABC is all positives in my mind. The ABC allows you to build a bridge not over traffic, and that's a big deal, because when you're building over traffic, you have a lot more risk. You have to deal with workers that are in traffic, next to traffic, and it's just a much more dangerous situation. When you can build something in a controlled environment where there is no traffic, the area is restricted to only construction workers. It's just a much safer environment. And so as far as the actual construction of the bridge, ABC is great. The guys that are doing the work, they're not, first of all, they're not in the traffic area. They're away from traffic. It's also it's also better for the public, because there's no impacts to traffic. No traffic restrictions, no lane closures, no detours. That's a win-win. Construction and public, a win-win. The other benefit is the bridge is just moved in typically in less than 24 hours. In this case, I think it was just a few hours. The bridge is moved overnight, and the next day you have a bridge where the previous day there had not been one. And it involves just a closure of the roadway for that duration of the move. That's great. To me, that is so much better than having to build anything over if it's even a highway, or even if it's a waterway. It's just a much better. I mean, in a waterway you wouldn't be able to use you can transport the bridge over water with SPMTs, but with land crossings, the ABC method is fantastic. I've actually observed it happening, and it is cool. It's probably cool for like the first 5 minutes, because the actual move is these transporters they're moving such a heavy load. They're moving really, really slowly. I mean, probably less than a mile an hour, maybe half a mile an hour, or even less than that. They're moving so slowly you can barely even see the wheels spin. The wheels are turning. So it's interesting for, like I said, the first 5-10 minutes, and then there's a lot of standing around, and the guys doing the work they're the operators of the towers. They're using the remote controls, and they're operating. And probably the trickiest part of the ABC is actually the move itself. And the companies that specialize in that, they have a lot of experience doing that work. The hardest part that I've seen with the actual move itself is when there is a rotation involved. So if the bridge needs to be spun, let's say 90 degrees in this case, you have to coordinate the SPMTs to rotate together. So, and if you're pivoting, the pivot point, the tower that's pivoting, it has to rotate at a slower rate than the outside of the pivot. So in that case, it can be tricky when you're pivoting. But aside from that, it's pretty straightforward, and it's really a great method. In this case, you had an overhang because the SPMTs were not exactly at the ends of the span. But if that's accounted for in the design, the SPMT move itself is pretty straightforward, and it's been tried and true. It's been tested at this point with many hundreds of bridge moves throughout the world, and I think it's the future. I don't see this being reduced because of this collapse. If anything, there's going to be more of this, and it's also probably, well, I know it is. It's cheaper. It's certainly cheaper because, as mentioned, you're not dealing with traffic. You're not impacting traffic. You don't have to put any detours up. It's just really a fantastic way of putting a bridge in its final position. The third theory that's been put out there for the reasoning for why the bridge may have collapsed is a lack of redundancy. And the lack of redundancy is illustrated by the fact that when one member in a truss fails, the entire span collapses. All right. So in this case, a diagonal member failed, it seems, and the whole bridge collapsed. So that's going to happen for sure. And if any member failed, that would happen. Now the theory's been put out there. Well, there should have been more redundancy, and so I guess the idea is that if you had two trusses instead of the one, that would have increased your redundancy. So let's look at that. If I had, instead of this configuration, so this is my truss here, if I had a truss here and a truss here instead of a truss here, so now I have two trusses. I have two of these trusses on either end of the deck. Would that increase my redundancy? And now the answer to that is actually no. So if I had this setup and one truss member failed in this truss, so let's say the same diagonal failed in this truss, this truss has now lost its load carrying capacity. It fails. The entire truss fails. So now you lose this truss. You still have this truss, but you have an unstable structure because you have one truss supporting a deck that is not supported on its other end. So in that scenario, you would fail the bridge. The whole bridge would fall. This truss may have been left standing, but you would lose this and this deck. So if the design had included two trusses and one member if that same member had failed, the bridge still would fail, and you would have had a collapse, and you would not have averted a tragedy. So really, to make this redundant so that a collapse would not occur due to a failed member, you would have had to have three trusses. 1, 2, 3, let's say, as an example. Now, in reality, do you see three truss bridges? No. I have yet to see one. The trusses that do exist they're older, they're steel typically, they are two truss bridges. So you have two of these. They're not concrete. They are steel typically. But if they're steel, the same scenario applies to what happened here. You lose one member in a steel truss, you lose the entire span. So the idea that the lack of redundancy was an issue in this design, it's true. It does not have the redundancy that another type of bridge configuration would, like a multi-beam configuration where you have, instead of trusses, you have beams and you have multiple beams. So if you lose one beam, you still have 5 or 6 other beams to carry the weight. That's true, but in a truss bridge, such as this or existing trusses, they typically are not redundant. So that's considered in the design, and when you maintain and inspect those bridges, you account for that. You're looking for issues that could cause a failure of a member. But that lack of redundancy is not unusual, but it is in newer designs. We do try to account to not have that scenario. So in my opinion, the reason this design was approved and was constructed is because it was intended to carry only pedestrians. And that changes things because pedestrian loads are much lighter than vehicles. This design would have never been approved for vehicular traffic. It was carrying pedestrians, 90 pounds per square foot, much lighter load. The designer must have felt there's more liberty to try something that is not as redundant because the loads are smaller, and I think that was the thinking here, and it makes sense to me. When you're dealing with cars, you're dealing with traffic. You're designing for heavy trucks. You're designing for semis, 36-ton semis or more. So you're looking at much heavier loads, and this redundancy, this design, this design would never have worked for a vehicle traffic anyway. So let's just get that out of the way. So this design was specifically intended for pedestrians and the lighter loads that they involve. A fourth theory that has been put out is the fact that concrete was used instead of steel, and that precipitated the collapse. Now, it's true, steel is a stronger material than concrete. You do not need as much steel to span the same length as you do for concrete. So in this case, the bridge weighed 950 tons for concrete span of 175 feet. A steel structure would have weighed significantly less, maybe even 8 times less. So instead of 950 tons. So that's true, and you can't argue that. But the fact that it was concrete does not mean that the bridge should not have been built, that it would not be a successful design because of the material choice. The concrete is not the reason the bridge failed. There was some design mistake or a construction mistake that caused the failure. Now, it was certainly a heavy bridge. 950 tons for 175 feet is a lot. But that is not why the bridge failed. You can design anything and make it work, and as long as the design is done properly. So the fact that it was concrete, yeah, we can question that, and that's fair. But that's if the design had been done properly and everything in the field was done properly, it should have stood. No reason for it to not work. Okay, so that theory, yeah, you can argue they should have used steel, and there's benefits, of course, to steel. You can use a lighter foundation because you have less weight. Your piers could potentially be smaller. So there's benefits to steel, but in this case, the owner was happy with the concrete, the way it looked, and that's the way they decided to go. So, again, you can argue, but at the end of the day, if concrete was chosen, you can certainly have made the design work for concrete. All right. Now, the fifth theory that has been also put out there is the fact that the bridge, which was a 2-span bridge, was missing its second span, and that this second span, it was not installed yet, so the bridge did not have the full capacity. So when you look at the drawings, this is the span that was installed. This span was yet to be installed. So the fact that this was not installed, the theory goes, it affected this span, the strength of this span. Okay, so that again is simply not true. This span and this span, these are two distinct spans. They are simply supported spans that are not dependent upon each other for stability. So this span had its own bearings, had its own support system at the piers, and so did this span. So they were completely independent of each other. So this span if this span had been installed and this span had failed, this span would have remained standing. This did not contribute whatsoever to this. And in fact, there is a detail where we can see how the two spans were joined. This is the end of, this is over the pier, and this is the end of the one span and the end of the what they call the back span. And they did have, to close the gap between the two spans, they had a closure pour, and that was just to give the surface a uniform finished look so that there were no gaps. But they did have installed a couple of bars at the top to tie the two spans together, but these two bars were not enough to have the two spans joined and acting as one. So again, I want to stress this is the only detail that shows any sort of connection between the two spans, and this is not an adequate connection to make the two spans actually act as one. So they were not acting together. It would have just been, it was designed that way as well. It was designed as two separate spans that acted completely independently of each other. Final theory for why the collapse may have occurred is the idea that the post-tensioning cables were loosened in member number 11, and that was tweeted by, I believe, the Senator Rubio, and immediately following the collapse. So let's look at that theory. Now, this theory is actually true. So, and it makes sense why the post-tensioning bars may have been loose. So if we look at this member here, the one that failed, member number 11, when they post-tensioned the member, they had the member sitting on these false work towers. They post-tensioned the member, so at that point the bridge weight is being supported by the false work towers. So this member is very slightly in compression. So when they applied post-tensioning, that member is not seeing much compression because the weight of the bridge is being carried by all these towers. So when they squeeze that member, most of the compression being applied in that member is because of the post-tensioning. So the post-tensioning happens, the bridge is then put on the towers, the SPMTs, and moved into its final position. So now in its final position, the bridge just has two supports at its ends. Final position, the bridge has support here and here. And now, in that scenario, this member 11 is seeing a significant increase due to self-weight compression. That compression force now went from, due to the self-weight, went from being really, really small when the bridge was sitting on false work to now being significantly higher than previously. So with that large increase in compression, suddenly those post-tensioning bars are there's a additional squeeze that takes place. So those post-tensioning bars actually lose some of the tension. It makes sense. You add compression to a member that's not in compression. Now that member goes into a big compression, so it's squeezed. It gets shorter. Those bars lose tension. So in that case, that theory makes sense. Those bars lost tension, and it should have been accounted for in the construction sequence. Those bars losing tension, and it seems like when those bars lost tension, the contractor was out there at the time of failure tightening those bars up again. We've discussed in my previous parts of this video series why the contractor may have been out there tensioning the bars. We're questioning why he was out there at all tensioning the bars. That is going to be answered by this investigation. But the idea that the cables had gotten, that the post-tensioning bars had come loose is a valid theory, and it makes sense looking at the construction sequence. So those are the myths that I've debunked, and the final theory I feel like I've it's acceptable, it makes sense, so we can approve one of the theories that's been put out there. There's been just a lot of misinformation, just a lot of ideas that are being put out there, and people are latching onto them, and just it's being approved, and everybody's getting excited, but a lot of them are they're just not accurate. So we'll find out when the investigation concludes. We'll find out what happened and in detail, and so hopefully you guys have found this interesting. I've enjoyed going through the theories and giving you my takes. So I'll put out another video series here soon. I would like to add, if you guys have any topics that you would like to see me cover regarding structural topics, structural engineering, or any sort of structure topics. It could be about your home, it could be any bridge related topic. I'd love to hear your feedback. I'm not going to, I don't see myself continuing with this pedestrian bridge idea here for much longer.